Hi everyone, here's a quick video on how to calculate tipping force, the amount of force required to tip something over. Obviously this is of great interest to engineers and architects and the like. You don't want to build a house or a shed or anything and not know when it will tip. You've got to know how much force is required to tip something over for safety reasons and a whole host of reasons, right? So let's go at it quickly. This won't be a full analysis via physics. That's knowable, that's doable, and it involves some background though regarding Newton's laws and torque and all the rest. So I'm just going to go after it in kind of a simple fashion, and like we did in class. Basically, if you're going to tip this, let's just say this is a box, and you're going to tip it over by pressing near the top somewhere. If you press there, there will be some amount of force that will cause the box essentially to rotate around this point here, and the box will rotate and tip over. And how much force is required depends on some things, right? So I think a lot of this can flow from common sense. For instance, if you pushed here to tip this box over, if it's a heavy box, well, if this is the same geometry, the second box has the same geometry, but it's just a lot lighter. Well, it's going to be easier to tip over, right? Light things are easier to tip over. So this would require, if that's a lot of force, this would require less force. Right? Light things are easier to tip over. In PLTW, they don't call it F for force, they call it T for tipping force. So maybe I'll just do this. Tipping force would be low there, and the tipping force would be higher. It's harder to tip over heavy things, and it's easier to tip over light things, right? So what we say is that tipping force goes up if weight goes up. It's harder to tip over heavy things. So we say tipping force is proportional to weight. Okay? If it gets heavier, if the weight goes up, the amount of force required to tip it goes up. All right? What if you have two boxes that are equal in weight, but their geometries are different? Let's say in this case, one's taller than the other, and you press here with some force, tipping force. I'm going to drop that F subscript here. The tipping force there. Would you have to press with less force or more force to tip this one if you pressed it up higher? Right? And so if they're the same weight, so let's just strike the weight as being the same. If you're going to press up here to tip it over, well, if they're the same weight, that's going to tip more easily. Right? If you press higher, it's going to tip more easily. And if you're having trouble envisioning that, just picture sort of an extreme. If you're going to tip this box over, let's just talk about this one here. What if you pressed down here? What if you pressed right there to try to tip it over? That'd be really hard to tip it over. Trying to get it to rotate around this point right here. And so if you press here, you'd have to press really hard to get it to tip. And the higher you go, the easier it is to tip over. Okay? So tipping force actually goes down when the height goes up. So let's call this H, height. Up here, I didn't define weight. Let's define W as weight. Let's define H as height. Okay, and so if you press higher, you don't have to press as hard. Basically, it's a question of leverage. You get more leverage the higher you push. If this was really tall, you could probably just flick it right over. Right, so we say stuff like the tipping force. Well, if height goes up, tipping force goes down. So that's an inverse proportionality. Right? If height goes up, tipping force goes down. Okay, and the final consideration is what if you have two boxes that are the same height? You're going to press here, let's say, you're going to press here with a tipping force, some amount of force, and at the same height, you're going to press on this one, same height. Well, which one's easier to tip over? The same weight, same height. Which one's easier to tip over? I think we'd be real quick to agree that this is going to tip over more easily. This is going to tip over more easily. It's thinner. It doesn't have a big, wide base. Right? If you wanted this to be stable, you'd want to put a big wide base on it or something like that. Right? This is going to tip more easily than a wide one. Right? And so what we do here is we take a measurement, and the full analysis comes from physics. We're not going to do it. But you measure from the center of mass to the edge that you're going to tip. Right? So if we're rotating around that point, we're going to measure from the center of mass to the edge. And we're going to call that D for depth. I'd be tempted to call it width, but we already have a W for weight, so let's call it D for depth, that dimension there. And it's half of the overall width. Now this can get complicated if things have strange shapes, right? If the center of mass is not at the geometric center, this can get a little bit wacky, a little bit complicated. But we, in this course, are only going to deal with things that have their center of mass, it's called a COM, the center of mass at the geometric center. So whatever you're given for the width, just divide that by 2, right? So let's say this box was 12 inches wide. I would call D 6 inches, right? Just from the center of mass to the edge, not the whole width, right? And likewise, look at this one. If this had, let's say the whole width of this one is, 4 inches. Well, then the whole width is 4 inches. Well, then D would be 2 inches. Okay, and so we're probably pretty quick to agree that this one's going to tip over first. When D is smaller, tipping force is smaller too, right? So T is proportional to D. And what that means is if the width goes up, the D, if the diameter, or rather the depth, if the depth goes up, if that width goes up, the force goes up too. Okay? Now all we have to do is take our 3 statements that heavy things are harder to tip over. If you press higher, it's easier to tip over. And the wider it is, the harder it is to tip over. We take these 3 statements that I think really make sense to me in a real world common sense level, and I just combine them. So T goes up as W goes up, T goes up as D goes up. So I'm going to say tipping force goes up, and both W and D go up. But tipping force goes down if height goes up. So this is the formula we're going to use. If weight goes up, tipping force goes up. If the width goes up, the depth, as I've been calling it, the depth, center of mass to the edge. If the depth goes up, if it gets wider, it's harder to tip over. You need more force. But the higher you press, the less hard you have to press. If H goes up, the height of the press, then the tipping force goes down. Okay, so let's try to put this to use. Quick example here. I'm just going to put my formula right here so I have it handy. Tipping force is W times D divided by H. Okay? So how much force is required to tip over the box pictured below if it weighs 10 pounds and then 20 pounds? And, I didn't give it a height, did I? We need dimensions here. Sorry about that. Let's call this 12 inches. Let's call this one 8 inches. And let's call the height, gosh, I don't know, how about 16 inches? I should have done that already, but there it is. No big delay there. Okay, sorry about that. So how much force if it's, so A, well the tipping force will be, let's see, weight times depth. And so this is at F1, right? F1 is this one here. So we're going to tip it, we're going to push there and tip it back that way, right? And so T is going to be weight, which is 10 pounds, 10 lbs. The depth is so we're tipping it, we're pushing here, so we're tipping it along, this is our base of support here, 12 inches. So I'm going to put half of that, from center of mass to that edge is 6 inches. 6 inches divided by the height of, let's see, we're going to press, let's just call the height pretty much right at the top, 16 inches. Right? So 16 inches. Now right off the bat, you see that inches are going to cancel out. In terms of our units, the inches are going to cancel, and our answer is going to be left with the unit of pounds. So 10 times 6 is 60, right? So 10 times 6 is 60, and 60 divided by 16 is just under 4, yeah, 3 3/4, 3.75. So A, 3.75 pounds would tip that box over. Okay. For B, what if it's 20 pounds at F1? Right, so what if we press, what if the box weighs 20 pounds and we still press there? Well, do you see what's going to happen? That's going to turn into 20 times 6. So not 60, but 120. Right? So if I double that, then this becomes 120 over 16. And 120 over 16 is going to be, 7.5. So for B, it's just the weight went up, 20 lbs, 20 pounds, but everything else is still the same. 6 inches is the distance from the center of mass to the edge, and we're pressing about 16 inches high. Right? So when you run this number, the tipping force will be twice that value, because all we did was double that numerator number. Right? So this won't be 3.75, this will be twice 3.75. You can go ahead and run the numbers, I'm not going to. Because 7.5 pounds will be the answer. Okay, 7.5 lbs would tip over that one if it weighed twice as much. And that makes sense, weighs twice as much, you've got to press twice as hard to tip it. What if we press here? How about applying the force at F2? So tipping it over that way now, we're going to rotate it around this edge. And our center of mass is there. And so we're interested for D in this number right here, half of 8. And this is going to be, use your common sense to double check, is it going to be easier or harder to tip the box over? Well, I think it's going to be more easy to tip it over if we push this way as opposed to pushing that way. And let's see if that all pans out, right? So T equals weight times depth over height. Okay, so let's just do it for the 10 pounder. So the weight is 10 pounds. But look at D. Before D was 6 inches, but now D is only 4 inches. 4 inches, so it will be easier indeed. And we're going to press at the same height, the 16-inch height. Right? So 10 times 4 is 40. And 40 over 16, let's just get the right number here. 40 over 16, 40 divided by 1/6 is 2.5 pounds. Right. So only 2.5 pounds will tip it over. If you press here at F2, that's going to tip it that way. And if you want to press at F1 to tip it over, if you want to tip it sort of that way, you need to press harder. If it's 10 pounds, 3 3/4 pounds. And if it's a 20-pound box, twice that, 7.5 pounds. Oops, I just drew these arrows and had them covered up by the calculator. If you want to tip it by pressing at F2, if you want to tip it that way, that's going to be easier. Right? That's a lesser depth. And if you want to, if you want to tip it on the long axis, that's going to be more difficult. 3 3/4 pounds if it's a 10-pound box, and 7.5 pounds if it's a 20-pound box. All right. So there's a quick intro to tipping force. Right. All you're doing is you're multiplying the weight times the depth, and the depth is half of the width. Right. The depth is half of the width. And then you're divided by the height of the push. And that's it. There's tipping force in a nutshell. Okay, go solve those problems. Email me if you have any questions at all.